When I was little, my father was famous. He was the greatest samurai in the empire. He cut off the heads of 131 lords.
Hey everybody, Jerry Williams, aka Greater Sapien here. It's currently Tuesday, April 6th. I'm not sure what day I'll upload this. Anyway, it looks like last night our old friend Todd Peachey popped his head up on the last video where I ran him through about his poor understanding of momentum. It's taken him a couple of months, but he thinks he has a rebuttal to me. Problem is, he tipped his hand in the comments, so I'll just record a pre-rebuttal now before he's made his video. What he's going to do is move the goalpost, change the parameters of the scenarios he set up. Feel free to check out the videos in the description to get caught up on the exchanges, by the way. Up until now, the collisions discussed in the videos were presented as perfectly elastic collisions. In Todd's initial video, he spoke of cars being knocked away, which I noted must mean the cars are indestructible and no energy was lost due to sound or heat, and it must be an elastic collision.
The parked car is going to stop that car dead in its tracks. Now what's going to happen when this car hits that parked car? It's going to send it sailing down the street.
Now, we know in reality both cars are destroyed, but I think in his scenario, these cars are perfect, unbreakable objects. Now, this is a perfect system, so all the momentum is conserved for us to see. Nothing is lost to sound or heat and distortion, and it's all there. So if there's a perfectly elastic collision, all discussions from that point on are done from that point of view. But Todd, in his comments, has tipped me off that he now wants the collisions in the moving Earth scenario to be inelastic, so that the cars will stay together and all that. He pointed out that he went to the Khan Academy website and got this info. So, haha, Greater Sapien, the cars will stay together. Well, yeah, in an inelastic collision, a perfect one, but that's not what we had up until now. And they'll also stay together if the Earth isn't moving. It's the same either way. By the way, when I wrote this, I told myself I had to slow down my normal rapid fire because an elastic collision sounds too much like an inelastic collision. Now, I'm glad Todd is actually trying to learn things by going to Khan Academy, but he's not going about it the right way. He copied the text from Khan Academy, and there's nothing wrong about that text, except what he did was he took an answer a user gave on a message board, not an instructor. Now, this guy's answer is right about inelastic collisions, but this tells me Todd is going to Khan Academy looking for support of his claim, not to learn. And so he saw something that fit, and even though it changes the parameters of the discussion, he used it. Now, before I go into what Todd should have learned from Khan Academy, let me bring up my responsibility in all of this. My error. My mistake was in meeting him where he was instead of taking him to where he needed to be in terms of understanding. I've said it before, simplifying things for the sake of clarity is a nuanced thing and can be quite helpful, but also problematic. Such is the case here. For example, for the ease of Todd's understanding of the math, I came up with the term momentum units. Not the best choice, I know. But my biggest error was allowing the conversation about conservation of momentum of these moving objects before and after collisions to conflate momentum with kinetic energy from time to time. I think momentum units might have done that. In a perfect elastic collision, both momentum and kinetic energy are completely conserved. So conflating them isn't as much of a problem, something I can usually separate in my head. But Todd doesn't have that understanding, so in not making them distinct, I muddied the waters absent-mindedly. I even conflated them in a recent comment, and man, mistakes happen when you simplify too much. And now, because Todd decided to make it an inelastic collision, when he doesn't have the ability to distinguish kinetic and momentum, everything goes sideways. Conflating them needlessly, that's on me. But changing the parameters of the discussion is on Todd. Todd decided the collisions were now to be inelastic, But when he went to Khan Academy, he didn't read what they presented and only picked what he wanted. If he had, he would have seen this, showing an elastic collision was exactly what I was describing. And he would have seen this breakdown of the differences between elastic and inelastic, again, supporting my description of elastic. And what he also would have noticed is that none of the examples they show on that teaching site have any concern about whether or not the entire system is moving, if they're on moving surfaces or not. No, it's only concerned with the interactions of the objects themselves. Outside doesn't matter, which supports my point. Elastic or inelastic isn't a problem really, except he's not going to go back and look at both a non-moving Earth scenario with the same type of collision. He hasn't made the video yet, but I'm pretty sure he's going to solely focus on an inelastic collision on a rotating Earth. He won't compare it to one on a stationary Earth and discover it's the same. To be clear, what I'm saying is, it doesn't matter if a collision is inelastic or elastic when it comes to the Earth being in motion or not. The results of an elastic collision will be the same whether the Earth is in motion or not. And separately, the results of an inelastic collision will be the same if the Earth is in motion or not. He will try to mix them up in order to claim I'm wrong. So I'll break it down for him here. And this is not just for Todd. Seriously, this is for anyone trying to understand these collisions in inertial reference frames. A system that is not in motion and one that is at a constant velocity are both inertial reference frames, so interactions within them will act the same. And honestly, my real mistake was not doing this video from the start. But hey, here we are. I'm only going to do one collision, but it could easily be applied to others. The collision is two objects, cars, whatever, approaching each other at a rate of 2,000 miles per hour that collide at a specific point over the Earth. We'll look at both perfectly elastic and inelastic collisions over both a stationary Earth and a moving one. And we'll see that the motion of the Earth does not affect the outcomes. That is, though elastic and inelastic collisions have different results, the results are not affected by the motion of the Earth, which is the whole point of this discussion. Todd's claim is that if the Earth were in motion, we would be able to tell because collisions like these would result differently. And what I'm saying is, no, they won't. You can't tell if the Earth is moving or not from these collisions. So let's get to it. Two objects moving toward each other. A is going 1,000 miles per hour east, B 1,000 miles per hour west. Earth is not moving. They will collide over spot C. The space between them is closing at 2,000 miles per hour, and they are each getting closer to spot C at 1,000 miles per hour. Before collision, what is the momentum in the system? If both objects have a mass of 1, the momentum is mass times velocity. So A has momentum of 1,000 and B has momentum of negative 1,000 because its velocity is in the opposite direction. Add all that momentum up and the system has zero momentum, right? Okay. Now, what about kinetic energy? Object A is going 1,000 miles per hour east and has kinetic energy of 500,000 because kinetic energy is half mass times velocity squared. 1,000 times 1,000 is 1 million. So 500,000 in kinetic energy. What about B? Is it negative 500,000 balancing object A? No, it's positive 500K. Why? Because even though it's going in the opposite direction, kinetic energy is mass times velocity squared. Half of it. Negative 1,000 times negative 1,000 is positive 1 million. Kinetic energy is always positive. So total kinetic energy in the system is 1 million. Now, they collide over spot C. In a perfectly elastic collision, what I was describing in the previous videos, what would happen? Well, both momentum and kinetic energy are conserved in that type of collision. So we need the same totals after the collision. They start out with zero momentum, so after they need to have zero momentum. If they stay together, each object has zero momentum. Still zero, that works. But if they bounce apart at equal velocities, they balance out like before and it's still zero. Either way works for momentum. Now we deal with the kinetic energy. The system needs to end up with 1 million after the collision. Well, Momentum is conserved if they stay together or bounce, so it comes down to whatever scenario keeps the kinetic energy, which in this case would mean bouncing apart and going off at 1,000 miles per hour in opposite directions, keeping 1 million in kinetic energy and keeping the momentum 0. They separate from one another at 2,000 miles per hour, and they both move away from spot C at 1,000 miles per hour. That's a non-moving Earth. Let's move the Earth. Let's add 1,000 miles per hour east to the whole system. We add 1,000 miles per hour east to A, making it now go 2,000 miles per hour east. We add 1,000 miles per hour east to B, bringing it to 0 because it was at negative 1,000. The space between them is closing at 2,000 miles per hour, and they are getting closer to spot C at 1,000 miles per hour. Before collision, A has 2,000 in momentum and B has 0. Total momentum is 2,000. Object A has 2 million in kinetic energy, half of 2,000 squared, and B has 0, 2 million in the system. They collide over spot C in a perfectly elastic collision. So what happens? First, let's conserve momentum. If they collide and stay together and stop moving altogether, there would be 0 momentum. We can't do that. If they collide and stay together and both go off to the west, that would give each of them negative 1,000 for a total of negative 2,000. And we can't go from positive 2,000 to negative 2,000. If they stay together and go 1,000 miles per hour east, they both have positive 1,000 for a total of positive 2,000. That's the same, so that would be okay. And if A came to a dead stop and B went away from it at 2,000 miles per hour, that would be 2,000 in momentum, and that would work too. As for kinetic energy, this is a perfectly elastic collision, so we need to keep all the kinetic energy, all 2 million. We are limited by the scenarios that conserve momentum, right? So they either stay together and go east or separate. If they stay together and both go off at 1,000 miles per hour east, momentum is conserved, but A at 1,000 miles per hour has 500,000 in kinetic, and B has 500,000. That's 1 million instead of 2 million, so that doesn't work. But if A comes to a complete stop and B goes away at 2,000, momentum is conserved and A has 0 kinetic energy and B has 2 million for a total of 2 million, and that works. So, in that scenario, they separate from one another at 2,000 miles per hour and they both move away from spot C on the Earth at 1,000 miles per hour. And amazingly enough, that's exactly what happens when the Earth is not moving. Whether or not the Earth is moving, perfectly elastic collisions act the same. But what about inelastic collisions? What Todd is likely claiming is happening now. Will an inelastic collision be different on a moving Earth versus a stationary one? Let's look. Same scenario as before. Prior to collision, there is 0 momentum in the system. We have to stay at 0 on the other side. Prior to collision, there is 1 million in kinetic energy to spend, and we're going to get rid of all we can. This is inelastic, folks. There's going to be noise, heat, light. We're going to waste as much as we can. Let's try to get rid of 1 million. They collide over spot C. Getting rid of every bit of kinetic energy, bringing it to 0, means the two objects stop right there over spot C. No velocity. Can we do that? Only if momentum is also conserved. Total momentum prior was 0. Total momentum now is 0. We're good. This fully inelastic collision resulted in the two objects staying together, not moving, right over spot C, with a loss of 1 million in kinetic energy. Right? Great. Let's add 1,000 miles an hour to the system just like we did before. Here are the totals prior to collision. Object A has 2,000 in momentum, object B has 0 in momentum, for a total of 2,000 in momentum in the system. Prior to collision, object A has 2 million of kinetic energy and object B has 0, for a total of 2 million kinetic in the system. They collide over spot C. In this inelastic collision, we want to get rid of all the kinetic energy we can. So let's try to get rid of the whole 2 million, meaning they stay together and have absolute 0 velocity. If they have 0 velocity, that means they have 0 momentum in the system, where they had 2,000 prior. 2000 momentum can't disappear, so coming to a complete stop, losing 2 million in kinetic isn't an option. But what if they stay together but still have some motion? Just enough motion to conserve that 2000 value in the momentum slot, but lose as much kinetic as possible. If they stay together and move 1000 miles per hour east, they each have 1000 in momentum for a total of 2000. That works. Object A now has the kinetic energy of 500,000, and object B also has 500,000 for a total of 1 million. That's a loss of 1 million. Now, try as we might, we can't lose any more than 1 million and conserve momentum. So, here we are. The two objects are staying together, going 1000 miles per hour east over spot C, which is also moving 1000 miles per hour east, so the objects are staying right over it, not moving relative to spot C. And there was a loss of 1 million in kinetic energy in the process. That's the exact same result as the stationary Earth scenario. It doesn't matter if the Earth is moving or not. You can't tell. Now, someone might be yelling, hey, you didn't put the momentum or the kinetic energy of the Earth into those scenarios. And they would be right. I didn't, because it doesn't matter. I'll show you. Here are the collisions over a stationary Earth, elastic and inelastic, the values before and after collision. Let's add Earth momentum to the prior. We'll call it momentum Earth stationary. After the collision, has the Earth momentum changed? No, its velocity is the same, 0. So putting the same value here, the sides are still balanced. Kinetic energy, add kinetic Earth stationary to the prior. After collision, the same. Stick it there. Sides are balanced. Here are the collisions over a moving Earth, elastic and inelastic, the values before and after collision. Let's add Earth's momentum to the prior. We'll call it momentum Earth moving. After the collision, has the Earth's momentum changed? No, its velocity is the same, 1000. So putting the same value here, the sides are still balanced. Kinetic energy, add kinetic Earth moving to the prior. After collision, has the Earth's motion and kinetic energy changed? Nope, it's the same. Stick it there. Sides are balanced. Since the Earth doesn't change in any of the scenarios, we can ignore its motion. And that was the point of all this. He sent me a link to this GIF, thinking it was some kind of gotcha thing, stating one of these cars is traveling 2000 miles per hour west and the other is parked. Care to tell me which one? No, because you can't tell. That was my point. He just proved it. One of those cars could be traveling west at 2000 miles per hour on a moving Earth, and we're just rotating the camera, or one could be 1000 miles per hour west and the other going 1000 miles per hour east on a stationary Earth. They are approaching one another at 2000 either way. You can't tell. His point was you should be able to, but you can't. There are all sorts of ways that the Earth's movement can be detected. This just isn't one of them. And I'm sure that's why people like Todd want to keep going back to it. They want to say we should be able to tell if the whole system is moving through these collisions. And if we can't, that must mean it's not. Since collisions work the same in both moving and non-moving systems, they'll keep repeating this because it fits their claim. They could look into the deflection of the trajectory of ballistic projectiles in different hemispheres, but they won't. They could look at the difference in drop times in the east versus westbound projectiles, but they won't because their system can't explain it. But conservation of momentum and kinetic energy during collisions appear the same in either system because they are both inertial reference frames. So they'll use that and just lie about how it should work on a moving Earth. Now, I'm not even going to bother to watch Todd's latest momentum video when he gets around to it. I don't know if this video is dropping before or after his as I record this. I need to do some visuals. I write all this stuff without the visuals because I know how it all works, as do a lot of you watching. The visuals I make later to clarify for those who might need it. So it might take me another day or so to get this out. When his comes out, Someone let me know how well I predicted his claims. I predict he'll call me stupid 3 times and bonehead 4 times and so-called greater sapien twice. Doesn't matter. What he won't do is have an answer for anything I presented here. But maybe, just maybe, after seeing this, he'll go back to Khan Academy and actually pay attention to what's being taught and not just look for phrases that sound like what he wants to hear. You just know he won't.
That's my job! That's what I do! I don't lose! I win! Is there no one on this planet to even challenge me?
Maybe you came by to congratulate me on last night's victory.